So I'm going to talk about a project that we initiated back in 1995 in consultation with actually Dr. Bill Trush, and it's gone through a lot of different evolutions over time to the existing project that we have implementing today in association with our aquatic habitat conservation plan, which includes a variety of mitigation measures to one of the key goals is to try to minimize sediment, management-related sediment into our watercourses, with the basic premise that if we're shutting off the spigot with sediment inputs, we should be seeing less sediment coming in, so therefore more sediment moving out of these systems, and also a coarsening of the bed load as a result, with less fines coming into the system. So this is a project associated with our effectiveness monitoring. It's the Class 1 channel monitoring, the third item there, in addition to a lot of the other projects that we have. The basic objectives of this Class 1 channel monitoring is to document changes in stream morphology and selected depositional reaches of third, fourth order size basins. We wanted to collect data that will provide a better understanding of channel processes and stream dynamics as they relate to both management inputs as well as natural sediment inputs. We wanted to use long-term trends and key channel variable to assess these changes in sediment delivery. The general context of where we have these placed in the watershed, we're looking for depositional reaches, so we're trying to avoid these transport reaches. And so here's an example of one site placed right, basically the first depositional reach from the headwaters. In this example here, there's a transport reach as well as a transition reach, and so again, until you get to this first depositional reach. So we're trying to place these to avoid have a minimal lag between you actually have sediment inputs coming from the hill slopes when it actually might have a channel response. So one of the variables that we're looking at is pebble counts, surface pebble counts. We're looking at placing these at thowag crossovers, where you have basically the channel moving from one side to the other side, and you end up with sort of a uniform channel configuration. And we're setting up a grid configuration with 10 transects, and we're collecting 15 pebbles at each transect. So we end up with a sample size of 150 pebbles, and we end up with somewhere around 5 to 10 sites, reaches or sites per reach. And we're measuring the secondary axis associated with these pebbles. We're also doing a longitudinal profile survey using a total station, and we're measuring every 10 feet using a steady rod, and they're basically hopscotching up the channel, measuring the thowag elevation, so we're getting XYZ coordinates associated with these. This is a schematic of one of the surveys at Little River. We're basically putting in permanent benchmarks so that over time we're basically able to occupy the same point and get corresponding elevations over time. We basically survey up through the channel. We close the loop so we can basically get an assessment on the quality of the survey. Make sure it has high resolution. The red dots show where we've collected pebble counts. This is for 2013, and we had 9 sites at that year at thowag crossovers. We have 13 of these reaches that we're surveying every year. Again, we started back in 1995 as sort of one site as a pilot year, and we've added up to additional 13 sites that we're measuring. The methods of the longitudinal profile changed in 2002 from using an auto level with center tapes and measuring perpendicular from the channel to using this total station where we get full XYZ coordinates. So because of the differences in the methodology, it's difficult to align those profile data. So we're with the new methodology. So we're only, for this talk, presently we've only summarized the data back to 2002 to 2013. For the pebble count data, we've actually gone back to 95 and included data through 2014. So with the pebble count data, there's a variety of different metrics that has been done in the literature to assess these data: cumulative size distributions, histograms, medians, different percentiles, most commonly the D84 and the D16. Surprisingly, we didn't see much with quantifier regression as an analysis tool. We found that to be a very useful technique to analyze these data, so I'll talk about that as our methodology, but just to kind of refresh everyone's memory of looking at cumulative distribution plot. they're kind of the quantile regression that uses sort of the same principle. So on the y-axis we have the cumulative distribution, which is basically any percentile you can pick. We have pebble sizes along the x-axis. So this shows first year 1997 for Tectaw Creek. If you pick the 50th percentile, you can progress across and down, and you end up with about, what is that? About 45 millimeter. And then through time, if you look at 2014, at that same, D50, that it's about 65 millimeters. So visually, you can assess this and see that there's a coarsening in that particular particle size distribution. Another way to look at it is individual percentiles. So this is using your common D16 and your D50 and your D84, and you can just do a trend analysis to see that for this particular site, there was a positive trend in the particle size distribution for each of those percentiles. With a quantile regression, basically get the benefit of having an assessment of the entire distribution of the data rather than just individual percentiles. So what we did was a percentile steps of every 0.5%. And on the x-axis, so that percent, on the y-axis you end up with a slope, which is the trend associated with each one percentile. So, for example, if we pick the 50th percentile again, you project up and you look at the trend essentially, anything above 0 would be a positive slope, and so there, you can assess each percentile from that trend and see that the particles are getting coarser by approximately 1.2 millimeters per year. So this is sort of a trend analysis. The bottom graph basically shows the intercept of each percentile. So that's centered on the midpoint of the year of the data. So this is 1997 through 2014. So the midpoint is 2005. And so for that 50th percentile, in 2005, that particle was 70 millimeters. So you get sort of these two graphs, basically you can get the full range of the distribution and assess the significance of those slopes as well, which is the gray bars is the 95% confidence. So if those gray bars are not crossing 0, you know at each one of those percentiles that you have a statistically significant trend. The red lines basically are showing, if you were to use ordinary least squares regression, what that based on the mean would be. And which the ordinary least squares assumes a normally distributed data. Pebble count data is typically not normally distributed, so they violate that assumption. If it was normally distributed, that black line would fall within those red bands. So let me back up. So basically for all 13 sites, for 12 of the 13 sites, we basically saw this result where all the particle size distributions were getting coarser over time, statistically significant. Then we had one exception in Beech Creek, and as you can see, there's a zero shows up on this graph here. So at basically the 50th percentile, everything below the 50th percentile, there was a statistically significant coarsening of the particle sizes. It's non-significant, so you get to 0.8, and there was a statistically significant decline in this this percentile range. So if you were to look at the D84, for example, at Beech Creek, it would have a statistically significant decrease in particle size trend. And that's what this results show here with the quantile regression, picking the D16, D50, D84, which is, again, the common metric used to evaluate these. Moving on to the longitudinal profile data, this plot basically shows every year for a particular site. This is Little River, or excuse me, this is Maple Creek, and so you basically see over time that the foul wag is basically shifting within the channel reach. And to account for that, if you start seeing it, like for example in 1997, the stream channel was on this side of the bank. In 2012, it was on this side. And so in 1997, it clearly had a longer channel. And if you were to just start at 0 and plot this data out, you'd have an offset over time as you progress through the channel and you try to compare thowag elevations. You'd have a significant offset and assume that your channel may have scoured or filled, and it's just because you're looking at totally different locations in the channel. So to further illustrate that, I put 100-meter marks on the channel. So again, starting down here at the beginning, 0, and by 100 meters, you're off by about 10 meters between the 2 years. And this is just using 1997 and 2000 as an example. And by the time you get 800 meters up the channel, there's a 50-meter difference in position. So what we did was came up with a thowag averaging process, which basically looks at all the different years and comes up with an average position, this planimetric position of the thowag, and then snapped all the elevations onto that average thowag. And then you plot it. And then you can compare the bed elevations accordingly. So sort of the implications without the averaging process, you can see here, this is the 400 meter in 2007 plotted here, and this is the 400 meter plotted here. And as you progress, you can basically see two similar pools in 2007, and here it is in 2012, and you might think, well, it must have, this pool filled and then therefore it scoured here. Whereas, in fact, if you use the thowag averaging process and line up those positions on the channel, which is done here, here's actually the 400 meter mark on the centered channel, and here's the 800 meter mark on the centered channel. And these line up, and you can see that if you try to compare aggradation or degradation across these surveys, you're comparing individual units to units. So once you do that, you can then compare, do an average change in bed elevation, looking at bed scour or bed aggradation. And what we found, there's a couple example plots. This Maple Creek here, we use 2002 as the base, so that's a 0 point, and then you can see that 0 is consistent on all these graphs here. And here you see a trend. This is a trend analysis that through time there's a scouring of the channel elevation on the order of about 0.12 meters. And this is statistically significant. Beech Creek had a statistically significant increase of about 0.03 meters. And here's one of North Fork that had a lot more variability associated with it. This turned out this one was not statistically significant, but had a slight decline. So in aggregate, for all 13 sites, we had 2 sites that had a statistically significant increase in bed elevation. 5 of the sites had a statistically significant decrease. Those highlighted in green. The yellow are the increases. And the ones are not highlighted had no statistically significant change. And here's the slope, which again, on this analysis would represent change meters per year over the time period. So I guess in summary here, the Pebble count data, what we found was using the quantile regression. It's actually a very robust analytical technique that I would encourage everybody to use. It's kind of initially difficult to get your head wrapped around how it basically works, but basically 2 figures gives you sort of the full understanding of the range of the distribution instead of just picking a particular individual quantile. And it's, again, very robust to non-normally distributed data, which, again, all of our data was non-normally distributed for the Pebble count data. The slope for all the percentiles, which is good news, were significantly positive, illustrating a coarsening of the particle sizes through time. And this is true for all the regions. The one exception was Beech Creek, where there was still a coarsening at the finer particle sizes, which is obviously good for fish in terms of finds in the substrate for emergence and survival. But there's the larger size class had a slight decrease. So kind of put a fisheries perspective on this summary. So fines are typically defined in the literature as being less than 6 millimeters, and that's a significant value for egg survival and fry emergence. where you typically want to see less than 10% of the finds in that category. And in the last 10 years, we didn't see a single site exceed 10%. In fact, the average was about 2.6. For the longitudinal profile data, if you want to look at and compare aggradation and degradation over time, you really need to do some sort of planimetric Thalweg averaging process, which aligns the longitudinal analysis before doing those sorts of comparisons. We found that 2 reaches had a statistically significant increase in bed elevation, and that's about 3.8 millimeters per year, and that's averaged out over that entire stream reach. 5 reaches had a statistically significant decrease in bed elevation of 9.6 to 37.9 millimeters per year. So we saw a lot more scour than we did in terms of the bed change elevation. And then 6 reaches had no statistically significant change in the bed elevation. So where we're going next, so this is sort of some preliminary results. What we hope to do next is do some more work on the longitudinal profile data, similar to what Kirk was talking about with the variable looking at pools. So we want to look at average maximum pool depths, total pool area, and the number of pools in each of these reaches. And look at a variety of different covariates to try to understand what's driving these changes in pools through time, such as management-related effects like harvest amounts or erode effects, and look at also watershed morphometrics like drainage area, stream density, basin slopes, stream slopes, and then also a variety of different rainfall metrics as well. Rainfall intensities, how the arrangement through the storms. And with that, if I have any questions.
For those 5 reaches that you saw a significant decrease in bed elevation, if you had any sort of process-based explanation for why you saw that reduction, and if you also saw coarsening associated with those reaches, and if you think there's a relationship there.
Yeah, we didn't try to do any sort of correlation analysis to find out the why other than knowing that it happened. We did, for those 5 sites that decreased, the only site, all the particle size distribution for all the sites decreased with the exception of Beach Creek, and that's one of the sites that had an increase in bed elevation. But again, it was only at the larger, basically the softball size particles were getting a little bit smaller, but the fines within that reach were getting coarser. We do hope to get into more process-based when we get into the pool, the fisheries habitat component of the study.
Other questions?
Hi, Matt. I enjoyed your talk. I just wanted to, it just sort of dawned on me. I hear all this pebble count happening, and it seems to me you guys can figure out something better than that. I mean, with all the software and stuff, can't you just sort of take some photo images and process it through a computer and speed up your work? Have you given any thought to that, or?
I know we have explored photo imaging. I know David had explored that in the past, and it seems like there's a lot of work involved in even photo image processing as well. So it's, it is a lot of work to count. We're not 200, but we're 150, but we also have multiple sites within each reach. So it is a lot of effort to collect them, but we found a really neat analysis to to look at data.
Other questions? I just had a comment. I hope that your method section in your proceedings paper is quite thick, so that we can try some of these out.